Hello and welcome to Chemistry with Mr. Olson. Today we're going to do some stoichiometry review, and it's experiment C in our review packet. If you need to, go ahead and read it, but I've started out the equation here. The balancing is interesting. We need the balanced chemical equation, of course. And a hint is provided. There are twice as many moles of nitrogen monoxide formed as moles of water. So in other words, the coefficient of the NO is twice as much as the coefficient of the H2O. Here on some temporary scratch paper, I'm going to write in that information in algebraic form. If this is X, then we'll have twice as many moles of that. That's going to be 2X. Now, we can see that due to the nitrogens, these two coefficients will be the same, so that will be 2x. Now, and the tin, or the coefficient here, let's just call that y. And the relationship, the numbers of oxygens give us an equation that'll give us the relationship between x and y. So, I worked that out before. Let's see. How many oxygens do we have here? We have O3. We have 6 oxygens. So that makes that a 6. And here we have 2 times Y. Here we have 2X oxygens. And here we have just an X, single X. So that simplifies, well, let's simplify that. 6x equals 2y plus 3x. So if we subtract 3x from both sides, we get 3x equals 2y, or y equals 3 over 2 times x. The simplest numbers for which that works are 2 and 3. In other words, if x is 2, then y is 3. And so that allows us to fill in the coefficients. And let me do that in a different color. That would mean 3, 4, this is 3, 2x, that would be 4, and x, that would be 2. And if you check the balancing, it actually works. So a cute algebraic way of balancing. Many other ways to balance, but that's a nice result. Okay, so we've got this reaction. We're given some data. Information like how much the beaker weighs, beaker plus tin oxide. And let's do some math. How much tin do we have? Well, we take the beaker plus tin, and we subtract the beaker. And that equals 2.08 grams. Mass of tin oxide. Well, we take the beaker plus tin oxide and subtract the beaker. So, similarly, 37.52 grams minus 34.88 grams equals 2.64 grams. How much does the oxide weigh? Just the oxide part of the tin oxide. Well, if you take tin oxide and subtract the mass of the tin, you get the mass of the oxide. So 2.64 grams minus 2.08 grams, and we get 0.56 grams of oxide. Now I should be writing the chemicals here. This is the grams of SN. This is the gram of SnO2. Mass of oxide. Let's be very clear what we're talking about. We're talking about, actually, an oxygen minus 2 ion, the oxide ion. Okay, how many moles of tin? Well, we have the grams of tin, 2.08 grams of tin. So, we get out of grams of tin into moles of tin using the molar mass of tin. Molar mass of tin is 118.7. So 1 mole is 118.7 grams. Doing the math, we come out to approximately 0.0175 moles of tin. And the moles of oxide, similar calculation. We take our grams of oxide, which is 0.56 grams of O minus 2, and we multiply, let's see, we get out of grams of oxide into moles of oxide. Now, O minus 2 is an oxygen atom with 2 extra electrons. We're going to ignore the electrons, and here is the mass of that oxygen atom, also the mass of an oxygen ion, roughly, very probably still rounds to 16.0, since an electron is only 1/2000th of an AMU. So 1, 16.0, and, oh yes, let's remember to cancel our units, and if we do the math there, that comes out to 0.035 moles of oxide, of O2 ions. O minus 2. O with a minus 2 charge ions, oxide ions. Okay, using the moles of tin, calculate the moles of other chemicals. Well, if we know the moles of tin, and looking at our balanced chemical equation, 3 moles of tin gives us 3 moles of SnO2. Clearly, these two are going to be the same. The moles of tin equals the moles of tin oxide. So, going back, the moles of tin, exactly the same as the moles of tin oxide, 0.0175 moles, and that's of SnO2. Nitric acid. Now there we have to do a little calculation. Let's do this in another color. Let's try this. We take a given, our moles of tin, 0.0175 moles of tin, and we want to get out of moles of tin into moles of nitric acid, so moles of HNO3. Okay, so how many moles of tin give us how many moles of nitric acid? 3 moles of tin react with 4 moles of HNO3. So let's put those numbers in here. 3 moles of tin, 4 moles of HNO3. Cancel our units, do the math, and it comes out to 0.00233 moles of HNO3. There we go. Now, nitrogen monoxide, for every 4 moles of nitric acid used, we get 4 moles of nitrogen monoxide. So these two numbers of moles are going to be equal. We could use a conversion factor, but it's 1 to 1 basically, 4 to 4. So that would be 0.0233 moles of NO. Okay. Concentrated nitric acid is a 15 molar solution. Calculate the volume in milliliters of the concentrated nitric acid you need for this reaction. So we take, the equation we're going to be using is, of course, molarity equals moles over liters, and we want the volume, so that's the liters. So doing the algebra, liters equals moles over molarity equals, now this is the nitric acid, so we want the moles of nitric acid, 0.0233 moles of HNO3 divided by the molarity of the nitric acid, 15.0, and it's moles per liter. Here I'm going to write moles over liters, and that way I can cancel my moles. And then we do the math, and we get the number of liters, which is 0.00156 liters, which we can convert to milliliters, which is 1.56 milliliters of HNO3 concentrated. There we go. And let's see, clearly explain how the moles of tin and oxide verify the formula of tin 4 oxide. Well, tin 4 oxide has a formula of SnO2, and we would expect the moles of oxide to be twice as many as the moles of tin. So let's see. We would expect the moles of oxide to equal 2 times the moles of tin. That's what we'd expect. And let's see, what is the moles of oxide? Moles of oxide 0.035. Does that equal 2 times 0.0175? Yes, it does. Very good. Now, lastly, we have a gas problem. Assume the classroom's at a particular temperature and an air pressure. Gee, I know I'm going to convert that temperature to Kelvin, so let's take 42 degrees C plus 273, and we get 315 Kelvin. And let's see, we just have one time, so this sounds like a PV equals nRT problem. And it asks us for the volume in liters. So, starting way over to the left, volume equals nRT over P equals N. Now we're talking the nitrogen monoxide gas. We've got that value here. The number of moles, 0.0233 moles times R. We're given R. Let's do a nice long line, and then I'm going to draw R in a different color. Let's use green. 0.0821 liters times atmospheres over Kelvin times mole. So Kelvin mole goes on the bottom. nRT. T is 315 Kelvin, and P, which is given to us, 0.985 atmospheres. Okay, now we show some cancellations. Moles cancels moles. Let's use a different color. I like using different colors. ATM cancels ATM. And Kelvin cancels Kelvin. We're left with liters. Great, that's what it asked for. We do the math, and we get an answer of 0.612 liters of nitrogen monoxide. And there's our answer. If you got a slightly different answer, it's probably because you rounded an intermediate result. You should not round intermediate results. And that's our answer, and that's our review of stoichiometry. And I hope this is helpful, and I hope you have a beautiful evening. Ta-ta!